Thanks for introduction. Good afternoon, everyone. My name is Liang from Peking University. My advisor is Professor Renjie. I'm excited to be here to share with you how to build a tagging system with RFID to support high throughput and high reliability logistic scenario. This is a joint work with MIT, UCSD, and the Alibaba Group. Thanks for all great co-authors. We have witnessed the quick development of two consumer logistics. For example, Tmall of Alibaba delivered more than 1 billion packets during the Double 11 holidays, with an average delivery time of fewer than 3 days. Worldwide, people delivered more than 150 billion packets in 2020. So, how can we deliver more and more packets in a shorter and shorter time? Efficiency is very important. Scanning is the efficiency bottleneck in the logistic networks. We can scan all the packets with QR code under line of sight, but we cannot scan the packet if it is concluded by other packets. This is a fundamental limitation on QR code scanning. RFID, as a passive electronic tag, can work under even no line of sight with high reading speed. With RFID as the tagging system, we can scan all the packets even they are under no line of sight. It can largely improve the packet throughput, for example, from 1 packet per second to 100 packets per second. However, RFID suffers from cross-reading. In logistic scenarios like warehouse check-in gate, we only want to read the tags in the range of interest in the left side of the green line, for example. But we cannot control the reading range of RFID reader precisely. We may read the tags outside of the range of interest. This is the cross-reading. Cross-reading hurts reliability, and we must handle it. If we can locate the packets with RFID, we can determine whether it is in the range of interest and get rid of the wrong tags. So RFID localization kills RFID cross-reading, which ensures reliability. A natural question is, do we already have the perfect tagging system with RFID localization? No. Ideally, localization kills cross-reading and ensures RFID both high reliability and high throughput. But actually, state-of-the-art RFID localization systems only have insufficient throughput and insufficient reliability. The problems are that localization always brings time overhead. We can obtain the tag ID by just read it a single time, but we need to read it multiple times to locate it, because localization needs a higher time resolution or a higher spatial resolution in multiple algorithms. Also, the multipath effect imparts reliability. To overcome these questions, our solutions are, firstly, we design a new hardware parallel wideband sniffer to realize zero localization overhead. Secondly, we develop a multipath mitigation algorithm to optimize the longtail cases, especially errors caused by multipath. According to the regulations, an RFID reader can transmit at a power of 13 dBm in the ISM band. Although regulations are different across countries, ISM band is typically less than 26 MHz, resulting in a time resolution of only 6 meters. Previous workshop, RFID chip and antennas can respond to a wider band. We call it out of band, about 300 MHz. With out of band, we can locate RFID with a resolution of 0.5 meters. It is a great improvement. FCC regulations limit the transmission power of out of band to be lower than negative 13.3 dBm, which is too weak to active tags. An ISM band reader transmits high power signal and it can scan RFID tags, but it cannot locate the tag. On the contrary, the wideband reader is limited to transmit low-power signals. It cannot activate the RFID tag at a reasonable range. So what happens if we use both two readers at the same time? The tag will be activated by the ISM band reader, and it reflects the ISM band signal. It also reflects the signal from wideband, so both the reader can read the tag. Then we can scan and locate the tag successfully. Because the wideband reader only sniffs the signals, we call it wideband sniffer. Consider a conventional ISM band RFID reader with one antenna. It cannot make high precision localization. By using an antenna array and a wideband sniffer, we improve its spatial resolution and time resolution, resulting higher localization precision. Following the ideas of sniffer, we need to design a zero overhead sniffer system. To achieve it, parallelism is important. This is the system overview. The ISM band reader and the wideband sniffer work together to communication with the tag and collect wideband channel information parallelly. Then our channel estimator will perform correlation calculation and produce the channel matrix across all the antennas and all the frequencies. Finally, we locate the tag with our multipath mitigation algorithm. Our system has many design considerations. Due to the time limitation, we only introduce how to design the sniffer and how to design localization algorithm. You can refer to our paper for more details. We use multiple sign waveform to sniff the tag's wideband signal because it is adaptive to RFID narrowband modulation nature. Multiple sign means we use multiple sine wave at different frequencies to sample the wideband. We need to build a receiver to receive each frequency parallelly. At high level, we have two candidate designs. One is analog architecture, and the other one is digital architecture. The first one, analog architecture. We can copy the input signal by splitter and then mix them with different frequencies. After low-pass filter, each ADC only deals with a narrowband signal. Noting that we can change the carriers at different mixtures, so its work frequency is flexible. In this architecture, each frequency at each antenna needs one RF chain. Considering that we have M antennas and N carriers, we need M times N RF chains. Its scalability is bad. On the contrary, digital architecture down-converts the signal with only one mixture, and then it processes down-conversion in the digital domain. This architecture needs a high bandwidth ADC because it samples wideband signals. The advantages is that it only needs one RF chain for one antenna. To compare, analog architecture has less requirements on ADC, and it has higher frequency flexibility, while digital architecture has better scalability. We built two prototypes for testing. One is analog, and another one is digital. We evaluated their simple accuracy, latency, and channel estimation performance, almost the same. But debugging the analog system takes 10 times longer than the digital systems, considering we need a large number of antennas and frequencies. For high precision, for example, 8 antennas and 16 frequencies, if we use analog architecture, we need about 128 RF chains, while digital architecture only needs 8 RF chains. We think scalability is more important than flexibility in our applications, so we select the digital domain architecture at last. Specifically, in the final system, we leverage the advanced wideband transceivers in LTE 5G base stations, which directly provide wideband NQ stream to FPGA. Then, we design the downtown conversion and downsampling in Verilog. Then the compressed narrowband simples feeds to the host computer for future processing by the PCIe interface. We call our hardware platform RF-Chord because it transmits and receives multiple sign carriers like a chord in the music. With the parallel wideband sniffer, we can obtain all the wideband channel information within one read. We call it one-shot capture. There is no time overhead for our localization. Next, we will try to address the multipath problem. Let us see how multipath imparts localization. Typically, the received signal is a vector superposition of the direct path and multipath on the IQ plane. With a baseline algorithm, like hologram or music, we can initially estimate the direct path corresponding to the tag location ground truth. This estimate is not very accurate due to the multipath effect. It has an estimate offset from the true direct path. If we can determine this offset, we can correct the cross estimate. By subtracting the cross direct path estimate from the received signal, we can obtain a cross multipath estimate. Direct path estimate at the offset equal to the direct path. Multipath estimate at the offset equals to multipath. So there is an equivalent relationship between these two offsets. They are equivalent. If we can calculate the multipath estimate offset, we can know the direct path estimate offset also. Please refer to our paper for the details about the equivalence, but till to know, our task is to calculate the multipath estimate offset. We found wideband is very helpful to do it. The key insight is that multipath vectors are dispersive. That is, multipath vectors from different frequencies have different phase, thus different angles on the IQ plane. When there are enough number of carriers, they will be uniformly distributed on the IQ plane. At the same time, the multipath estimate offset is not very sensitive to the frequency, and their angle almost keeps the same. We prove it mathematically in our paper. So if we can add up all the multipath estimate, the multipath part will cancel each other out, and the offset part will be retained. Now we can get the offset, and we can use it to mitigate multipath to correct our direct path estimate to get a more processor's localization result. This is a lab test. With the baseline hologram algorithm, we cannot estimate the tag location correctly due to multipath. The error is 1.4 meters. By using our algorithm, we can mitigate multipath and reduce the localization error from 1.4 meters to 0.4 meters. With parallel wideband sniffer and multipath mitigation, we are approaching the ideal tagging system. The following is our evaluation. We evaluated our system in the lab environment. The setup included transmitters and receivers array, a sliding rail to move tags, and a total station device to collect the ground truth. We evaluated the throughput. As the sniffer requires the ISM band reader to activate the tag, the upper bound of this throughput is the same as the throughput of ISM band reader. We used the Impinj R700 reader. Its throughput is about 180 tags per second within 6 meters. The result shows that the performance of our system is close to the ISM band reader, achieving more than a 95% success rate, reading about 175 tags per second. It means that we can locate 175 tags per second. We evaluated the reliability. Sniffer deploys a large localization bandwidth compared with conventional RFID localization systems. We evaluated how it influenced the performance. We can see a larger bandwidth always leads to a better localization performance. From 15 MHz to 200 MHz, the median error decreased from 0.33 meters to 0.14 meters. And the 99 percentile error decreased from 2.4 meters to 0.79 meters. We deployed our systems to real-world logistic network of Alibaba. According to the scenario requirements, we designed 2 different systems, an 8-antenna pathway gate and a 4-antenna gate. Long-term data show that RF-Chord could achieve a localization throughput of more than 100 tags per second, 10 times faster than the concurrent fastest solutions. Additionally, RF-Chord can reduce the cross-reading rate to 3 in min 5, a 1,000 improvement to popular localization, popular logistic commercial RFID reader like Impinj X-band. In conclusion, reliability and throughput are the 2 most important evaluation dimensions of logistics tagging system. Localization kills cross-reading problems, so it improves reliability. RF-Chord, based on the parallel wideband sniffer and the multipath mitigation algorithm, can achieve high localization throughput and a very low cross-reading rate. We have open-sourced our hardware design, algorithm, and a small data set. Welcome to try it, and thanks again. With that, I'm ready for questions.